Okay, so let's talk about the negation of a universal statement. Okay, so if you're going to say not for every x in D in Q of x, okay, so the negation of this universal statement is there exists x in D such that Q of x is not true. Okay? So, those might seem like a bunch of weird symbols, but what are we really doing? If you want to think about this in this sense, this says, for every x in D, Q of x has to be true. But the negation of that statement saying the negative of this statement means there exists x in D such that Q of x is not true. So Q of x is not true for everybody in D. Okay? And then we have the negation of an existential statement. Okay. So the negation of an existential statement means the negation that there exists x in D such that Q of x is true. Well, the negation of this statement is that for every x in D, Q of x is not true. Okay, so what does this statement really say? It's saying, all right, so within this parentheses, it's saying there exists x and D such that Q of x is true. All right, well then the negation of that statement would be there does not exist any x and D such that Q of x is true. Or for every x in D, Q of x is not true. Okay? And so let's look at a couple of these statements. Okay. So let's say we had a statement that we knew is not true. We want to look at the negation of that statement. Okay? Let's say the negation of the statement that we know is not true is we're going to say, let's say, the negation of for every x in Z, let's say x is going to be greater than or equal to 0. Now this statement on the inside of here says that for every x in Z, x is greater than or equal to 0. I know that statement's not true. And so I'm going to look at the negation of that statement. Okay? And so, if you look at the negation of that statement, this is equivalent to saying there exists x in Z such that x is not greater than or equal to 0. Okay? So that Q of x is that x is greater than or equal to 0, and negation of Q of x is, well, x is not greater than or equal to 0. Okay? And so we do have negative numbers. Right? Now let's do a negation of a existential statement. Okay? So I'm going to take an existential statement, and I'm going to do that I know is false, and I'm going to do the negation of it. Okay? So let's say the negation of the statement that there exists x in R such that x equals a plus ib and b is not equal to 0. So we're on our new problem now. Okay, so the negation of this statement. So what is this saying? There exists x in R such that x equals a plus ib, where I is an imaginary number. So that would have to mean that complex numbers would exist within just the reals. But that's not true, okay? So the negation of this statement says that for every x within the reals, x equals a plus ib, and b has to equal 0. Okay? So this q of x, you see how it changed by switching that over into an equal sign instead of a not equal sign. As on the previous problem, what did we do for our q of x on, right, so look at the comparison of these two. So when you do the negation of the statement, you can see that, I mean, just symbolically, going from this statement to this statement right here, yeah, you're crossing out the inequality, saying that's not true, okay? And on this one, from going from right here to right here, we're removing the not equal sign and saying, well, b has to equal 0 because we don't allow any complex numbers in the reals, okay? Okay, so that's a negation of a statement. Now we have to consider, what if these became more complex? Okay, so we have the negation of universal statements. All right. And this gets more complex. So we could have a universal conditional statement. So a universal conditional statement says, well, for every blank, you can say if blank is true, then blank is true. Okay. Now these universal conditional statements end up appearing in math a lot, and this is a discrete math class, so we're going to look at, spend a lot of time talking about discrete series. So if I say, what is a universal conditional statement that is one of the more basic ones that we would go around when talking about infinite series? Let's say, so what is a universal conditional statement that applies to series? So for any infinite series okay, so given any infinite series, if the limit as n tends towards infinity of a sub n does not equal 0, okay, so for any infinite series, if this limit does not equal 0, then the sum n equals 1 to infinity of a sub n diverges. Okay, so this actually needs a proof. We're not going to get into the proofs of this right now. But think about this logically. So we're given any infinite series, okay? And I'm just looking at the terms on the inside of this. Let's say that limit as n tends towards infinity of a sub n equals 1. Well, what would happen to that series? Eventually it's going to become 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. It's just going to keep adding 1 off to infinity, okay? Even if it's just becoming infinity close to 1. That means that the inner terms that are adding up together, they have to go to 0, otherwise this thing is divergent. This is what's known as the divergence test. So the numbers have to start getting small for any infinite series to actually converge to a number, okay? So this is what's known as the divergence test, and it's a universal conditional statement that is true for infinite series. Okay, there are a whole. When it comes to universal conditional statements, in my mind, this leans itself very well into infinite series, and there are actually quite a few examples in y'all's book and in the homework that end up incorporating series. Okay, and one of the reasons that series will be incorporated into this class is because what are infinite series? They're discrete sums. It goes a1 plus a2 plus a3 plus a4 like that, all the way off into infinity. I mean, it goes off into infinity, but they're discrete in the sense that, yeah, it's just discrete sums, okay? So let's look at another universal conditional statement that applies to these infinite series, okay? So let's look at another one. For any infinite series, if the limit as n tends towards infinity of a sub n plus 1 divided by a sub n is less than 1, then the sum n equals 1 to infinity of a sub n converges. And this one, the one we did previously was the divergence test. This one right here is the ratio test. Yes?
Well, what was that supposed to be less than?
Less than 1?
Oh, that's just a 1.
That's just a 1.
Okay.
If that ratio is less than 1 as n tends towards infinity, well, then that infinite series is going to converge. And not just converge, it's going to converge absolutely. We haven't talked about what absolute convergence is. There are different types of convergence. But it basically means it's going to add up to some number. Okay? Well, let's put the other part of it up there as well. For any infinite series, if the ratio is greater than 1, then the sum equals 1 to infinity of a sub n diverges. And I think that'll make a decent video.